Hello students, today we'll be talking about formal charge and oxidation states, how they are being calculated, and how we can use the concept of formal charge to help us predict the best Lewis structure for a particular species. Okay, so in the first year in JC1, you learn about Lewis structures and how you can derive it from dot and cross diagrams. Yeah, but that is just a relatively sketchy way of determining the best structures, because you did not really go into details on how we can actually leverage on the concepts of formal charge. Okay, so today I will just going to illustrate to you on the board how it can be calculated. Yeah, so the first thing we need to do, right, is we need to understand the difference between oxidation states and formal charge. So formal charge should be something that is new to you in H3, although it's not directly in the H3 curriculum, but it's something that is good to know. Yeah, so in that case, I think I will need to formally introduce you to the difference between them. So for oxidation state, right, there is a very important assumption that we make. We assume a perfect ionic model. Okay, so what is the meaning of assuming a perfect ionic model? So that means that in a covalent compound, we will assume that the more electronegative element will take all the electrons in the calculation of oxidation states. So for example, I will use a very simple illustration. So for example, water, right? So for water, if you draw the dot and cross diagram, it will look something like this. Okay, so this will be the dot and cross diagram for water. I'm sure all of you can easily draw this out. Yeah, so between oxygen and hydrogen, oxygen is more electronegative than hydrogen. So in that case, if we assume a perfect ionic model, that means that oxygen will take all the electrons in the calculation of the oxidation state for both oxygen and hydrogen. Okay, so once we do that, a simple illustration is actually to draw a boundary around oxygen. So the more electronegative element will take all the electrons. Yeah. So if you do a quick calculation, right, you will notice that originally hydrogen has 1 electrons. Now it has 0. So it will take on an oxidation state of +1. Yeah, because it kind of like loses 1 electrons as a whole. So in the calculation of oxidation state, that's what we will assume. Yeah, so again, originally hydrogen has 1 electrons, now it has 0. So it takes on an oxidation state of +1. For oxygen, originally it has 6 electrons, now it has 8. So it will take on an oxidation state of -2. Yeah, so that is why in JC1 and maybe in secondary school, you learn that oxidation states for oxygen tends to be -2 in most cases. Of course, there were some exceptions which your teacher would have told you. For example, maybe in peroxide is -1, and maybe in superoxide is -0.5, that kind of thing. But I don't think we should memorize it. We can easily derive it. So for example, in hydrogen peroxide, so we'll try to draw the dot and cross diagram for hydrogen peroxide. So for hydrogen peroxide, it will look something like this. Okay, so we just alternate between the dots and the crosses. Yep, and then something like this. Okay, so yeah, so this is what you expect from H2O2. Yeah, so again, if we assume a perfect ionic model, hydrogen will lose all the electrons to oxygen. Yeah, but between 2 oxygen, there is no preference, so each of them will take back their own electrons. So when we draw a boundary, it will be something like this. And then so the other oxygen will be something like this. So you notice that in this case, oxygen has 7 electrons, so in excess of 1. So that is why in peroxide, it takes on an oxidation state of -1 for oxygen. And of course, hydrogen is still +1. And Yeah, so it's 2 plus 1 for hydrogen and oxygen. So this method of calculating, right, sometimes we call it the fundamental method of determining oxidation states. Yeah, so we can actually use this method to help us determine the oxidation state, in fact, for all compounds. So for example, if you are interested in determining the oxidation state, for example, methane, right, so you can easily do that, because for methane, it's like this. And carbon, of course, is more electronegative than hydrogen. Yeah, so in that case, if we just draw a boundary around carbons, so there will be 8 electrons in total, so in excess of 4. So in methanes, we were told that carbon has an oxidation state of -4 and hydrogen is +1. Yeah, and when we burn methane, it gives us CO2. And of course, carbon oxygen is -2 here, carbon is +4. Yeah, so sometimes you are probably aware of the fact that when we are dealing with carbon-based compound and natural compounds, natural resources such as fossil fuels, natural gas, right? We are really just playing with the oxidation state of carbon from -4 all the way to +4. Yeah, so +4 is the highest oxidation state which carbon can take. So whenever we are extracting energy from fossil fuels, this is really just the range of oxidation state which we are playing with. Yeah, but I don't think I will go into details on this, because that's not the purpose of today's topic on oxidation state and formal charges. Okay, so I will erase the one on methane first, and of course CO2. And we will now focus on how do we actually determine the formal charge of say water and H2O2. Okay, but before that, we need to understand what exactly are formal charges. Okay, so for formal charges, right, we will assume, okay, a perfect. So again, the keyword is perfect. Covalent model. Yeah, so we need to assume a perfect covalent model in order for us to determine the formal charge. Okay, so how do we do that? Yeah, so we're going to do the same thing. I'm just going to erase off this two because I think it's a little messy here. So these are calculation of oxidation state. Okay, so we have H2O2 and H2O. So I'm going to do the same thing. I'm going to draw out H2O here. So for H2O, it will look like this. Okay, so again, if if you assume a perfect covalent model, that means that there is no difference between O and H. So each of us will take back our own electrons. Okay, so in that case, when we draw the boundary, it will look like this. Okay, so same case goes for H2O2. So for H2O2, it will be like this. Okay, so again, perfect covalence model. So the boundary will look like this, and then like this. Yeah. So you realize that it's actually not very inspiring, because if you look at this, they are just taking back their own electrons. So in that case, the formal charge of hydrogen here is 0, oxygen is 0, hydrogen is 0, then it's 0, 0, 0, 0 all the way. Yeah, because there's no excess. Yeah, so in that case, when you look at it, it seems that formal charge is not very useful because it's not helping us in any way. Okay, well, that is because in the conventional language of covalent bonding, these are also called the normal covalent bond, when I contribute 1 electrons, you contribute 1, I contribute 2, you contribute 2. Yeah, but I think formal charge will come into play when we are dealing with situation when they involve dative covalent bonds. Yeah, so that is actually the topic for today. Okay, so I'm going to erase this again. And then I think from here, I'm just going to leave this on the board so that it does help you to formulate some understanding. Okay, so I'm just going to erase this. And then I'm just going to showcase to you the use. So for example, carbon monoxide. Okay, so for carbon monoxide, if you do the dot, if you try to work on the dot and cross diagram, it will look like this. Okay, so CO is like this. So this is carbon monoxide. Okay, so maybe I'll put the dots a little bit clearer. Okay, so again, if we look at formal charge, okay, remember we are looking at a perfect covalent model. So that means that any shared electrons, we will split them up directly, okay, or just split them up equally shared. Okay. So in this case, CO right in the middle, we just chop right in the middle, and then from here we can determine the formal charge of carbon and oxygen. So in this case, carbon originally 4 electrons, now it has 5. So in excess of 1, so it has a formal charge of -1. Oxygen originally 6 electrons, now less 1 electron, so formal charge +1. Yeah. So when we try to represent it in the Lewis structure, yeah, so CO will actually be represented this way. You notice that we don't draw out dative covalent bond for formal charges. Okay, so it will look like this. So this is the Lewis structure for CO, indicating the formal charge. If you choose to show dative covalent bonds, then you shouldn't be writing in the formal charges. So you should leave it as it is. Yeah, but after a while you realize that showcasing dative covalent bond have a little bit of limitation in the way you try to showcase chemistry. For example, in the drawing or reaction mechanism, you realize that it's a bit difficult to showcase in your arrow pushing, especially so in organic chemistry, because in most cases in organic chemistry, we do use curly arrows to represent the flow of a pair of electrons. So you realize a lot of limitation actually comes in. And actually this brings in, this comes in very nicely because in the H3 topics, which you're going to learn very soon, which is on reaction mechanism, you notice that from knowing formal charge helps you to minimize this gap in the way you push arrows, and you will be able to understand why, for example, a protonated ketone, the oxygen takes on +1 formal charge, and for a protonated alcohol, the oxygen takes in +1 formal charge as well. So I think it's easier for you to understand that based on based on formal charge, yeah, without memorizing, of course. Yeah. Okay. So so this is for CO. I'm going to illustrate to you another example. Okay. So I think I can use the board on the left. I think it's easier. Okay. So the other example will be NO2. So NO2 is something which you learn in JC1. So this NO2. Okay. So for NO2 again, the dot and cross diagram not so inspiring. So we have something like this, or like this. Okay, and of course we have like this, like this, like this, like this, and then okay. So in a normal H2 way of drawing the Lewis structure, you will simply draw it like this. Okay, so with a dot here. Okay. So this is what you learn in H2, and in normal circumstances, of course, not normal, in most circumstances, or in fact in all circumstances, you remark correctly. Yeah, but you realize that there is a bit of a limited way which you can sort of explain to people why is it that in NO2, right, the two NO bonds are actually equivalent in length. Yeah, so from in this case, we have to bring the concept of delocalization, we have to bring the concept of resonance, and it's a little bit difficult for you to represent it on paper because of the limitation of a Lewis structure. Yeah, then you realize that if I were to introduce the idea of formal charge, it's actually easier to showcase our understanding. Okay, so now let us try to calculate the formal charge of the individual species here. So again, we assume a perfect covalent model. So we will just shade like this, and then this is how it works. So remember that every shared pair of bond, whether is it double, single, triple, right, it must be split directly into half, and then each of the atom will get half of it. Yeah. So in this case, the oxygen on the left, formal charge 0. The nitrogen in the middle, originally 5 electrons, now it has 1 less, so it's +1. The oxygen on the right hand side, now in excess of 1, so it's -1. Okay, so when we try to draw out the Lewis structure indicating the formal charge, you notice that it looks like this. Okay, with a plus and a minus, and of course a lone electrons here. Okay, then you realize, this one looks quite weird. Okay, but actually this drawing, it fits perfectly, because from here, I can actually showcase my understanding or showcase the drawing of resonance structures. Okay, so you might have heard people or read textbook that the lone pair here can delocalize into the other oxygen. Okay, something like this. Okay, so this represents the movement of a pair of electrons, and this double arrowhead represent resonance structures. So from here, you notice that I'm able to show something like this, for plus, and then double bond O. Yeah, so I can easily explain why there's a negative charge here, because the oxygen has one excess so-called electrons. That's due to the dative covalent bond contributed from nitrogen. Yeah, so this is the way we try to I'm trying to share with you the advantage of understanding formal charges, because you are actually able to write out a structure like this. But of course, if you're coming from the perspective of H2, you'll be thinking that, hey, does it matter if I know formal charge? Can I explain it without showcasing resonance structures or without showcasing arrows? Actually, you can. You can actually do that quite easily by showing an orbital diagram. That looks something like this. So we have oxygen, and then we have nitrogen, and then we know that oxygen and nitrogen forms a pi bond like this. Okay, so this is the NO double bond. And then you also know that I have another oxygen here, which I'm going to represent in red. And then it has a lone pair here, which of course can also overlap continuously with the NO pi bond. Yeah. So a diagram like this will showcase the fact that N and the two oxygen has p orbital which are parallel to each other, and they can form a continuous overlap. And this continuous overlap will kind of give the NO an average bond length in between that of a double and single bond. I think a diagram like this would be sufficient for a H2 level, but for a slightly more advanced treatment, if you want to showcase your understanding of the fact that the real structure or the actual structure of NO2 is somewhere in between these two, or is a superimpose of these two structures, then I think showcasing the drawing of resonance structure and the use of formal charge will be extremely useful. Yeah, so that is the suggestion that I will have if you like to have a deeper understanding. Yeah, so knowing formal charges does help you with this. And then finally, I'm just going to again end off this particular session with how can we actually use formal charge to help us predict the best Lewis structure, okay, from let's say a few others, okay, which we have. Okay, so basically, whenever we try to showcase the Lewis structure, we want to minimize the formal charge that is so-called present in each atom. Yeah. So for example, in this particular CO, it has no choice because -1 and plus +1 on the left and right is actually the best. But are there other possible structures which we can have? Actually, yes. It is possible to have other structures. So for example, you will notice that I can easily cause this carbon to take on an extra pair of electrons. It is possible, but it will take on excess formal charge if you try to do a calculation. Yeah, so I think this is not advisable. So therefore, this whatever we have shown here using the triple bond would be the best formal charge or the best Lewis structure which we can draw for CO. Yeah, but what about other examples? So another example which I thought can be used is actually azide, which is N3 minus, which you often get in H2 exams, and it's actually the best way to showcase what exactly is the best structure for N3 minus. Okay, because in most H2 exam which you encounter, right, I think the easiest way to draw it is something like this, with a triple bond and then a dative bond, and then with a minus like that. Yeah, so this is really the easiest way to showcase this is the best so-called Lewis structure for azide. But after knowing or after learning about formal charges, you realize that this is actually not the best structure for azide, which I'm going to show you why. Okay, so how do you actually get this particular Lewis structure? You get it from, of course, drawing the dot and cross diagram. So something like this. Okay, and then of course like this, and then oops, sorry. Okay, so it has a lone pair. They did covalent bond to the nitrogen, and then we have 1, 2, 3, 4, 5, and then of course the excess electrons go to this nitrogen. That's why the overall charge is negative, something like this. Okay, but if you try to calculate the formal charge, you'll be quite surprised. Okay, so let's try to do that. Okay, so again, I draw a boundary here, I draw a boundary here, and then I draw a boundary here like this. Okay, so if you try to calculate the formal charge, the nitrogen on the left is 0, the nitrogen in the middle is +1, the nitrogen on my right is actually -2. Okay, why is it -2? Because if you calculate the total number of electrons around nitrogen, you realize that there are 7 electrons around nitrogen. So originally nitrogen has 5 electrons, now it has 7, so in excess of 2. So therefore the formal charge of this nitrogen is -2. Then you realize that if I'm going to sketch out the Lewis structure for azide, it will look like this. It will be 0, +1, -2. So you realize that it's actually not balanced in that sense. And then it looks quite weird because there seems to be like a triple bond on one end and then a single bond on the other end. And I'm not sure, for those of you who drew this, you'll be a bit unsettled because it doesn't seem like 100% right. Yeah, so of course, yes, if you're unsettled, you are not wrong, because truly this is not the okay. I mean, of course, we also have to showcase the overall charge to be -1. Of course, this is not the best Lewis structure for azide. Yeah, so the best Lewis structure for azide actually looks like this. So if you actually draw in the resonance structures, or you showcase arrow pushing, so it looks like this. The lone pair delocalized, so it forms a pi bond with the middle nitrogen, and then one of the pi bond and the triple bond actually break towards the nitrogen on the left. So yes, so from here, when we try to draw out a new Lewis structure of azide, you realize that now it looks very nice because what we have here is +1. Sorry, we have -1 in the on my left, so we have -1, +1, and -1. Yeah, so this would actually be the Lewis structure which best represent azide. Yeah, so therefore for azide, both NN bonds have the same bond length, and it's actually in between that of maybe of a triple and a double bond, somewhere in between, or maybe not even triple and double, but more like a double bond in that sense, because if you actually look at the actual structures from computational studies, you realize that it resembles more of this. Yeah, so more of a double bond between the two nitrogens. Okay, so with this, I hope you can, I think from here, use a very simple idea of formal charge to help you predict the best Lewis structures which you can potentially draw from whatever you start off with. I mean it'll be a good idea for you to maybe do a bit of practice. So for example, you can actually practice with NO3-. Yeah, so this is a good starting point for you to try to practice with. Then you can try to decide which is the best, what is the best Lewis structure you can draw for NO3- nitrates. And then of course, for nitrate, then you can sort of decide, okay, can I actually showcase that all the NO bonds are sort of equivalent by drawing the resonance structures? Okay, and then that will be a good starting point for you to practice on resonance structure drawing. Yeah, so from this very short video, I hope you are able to see, I think number 1, the difference between oxidation state and formal charge, and I think number 2, the advantage of using formal charge to help us predict a more accurate, so-called, maybe more accurate might not be the word, but maybe the best representation of a Lewis structure for a particular species. Yeah, and then as you progress on with chemistry, then you notice that you other tools will come in a little bit more useful. But in this case, I think formal charge at this point in time, I think it will help you to best predict the structure. Okay, so I thank you very much for watching the videos, and do look out for more videos in the future. Yeah.